octet rule gets brought up in chemistry, in introductory chemistry, and we keep it when we don't need it. The octet rule says that atoms tend to acquire 8 electrons, and that's a great talking point for teachers to start off with because it's very simple. There usually is a lack of purpose behind that, so what I want to do today is go through and show you why the octet rule is what it is, and why the exceptions are what they are, and how we're really a little misleading in the fact that we call this a rule. This is more that this happens a lot, and for reasons that are really irrelevant to the number 8. There's not something magical about 8 that makes atoms happy or somehow stable or anything along those lines, and we have a lot of misconceptions therefore about things like orbital filling, that's being stable when they're full, and things like that. So I want to go through today and show you why a lot of atoms acquire 8 electrons. What about them makes acquiring 8 electrons make a lot of sense, and why some things don't. So if we go through and we look at the periodic table a little bit, when we get over to things like fluorine and chlorine and bromine and iodine, a lot of people will say, you know, these have 7 valence electrons, and if they could just have one more, if they just had one more, they would have 8, and they would satisfy the octet rule. And therefore, these would all be happy. That's very misleading. There is a reason why these things end up getting 8 electrons, and it has more to do with the actual structure of these atoms. If you look at the drawings of these from a simple Bohr model, if we look at fluorine, fluorine has 9 protons. It has 2 electrons in its core and 7 in its valence. Now really to understand why the octet rule, you kind of have to understand trends. You kind of have to understand shielding, effective nuclear charge. So if you've never heard of that or seen those and you really want to have a good grasp on that, you should click on the link below and that'll take you to that video to show you those things first. But if you want to skip over that and just have a rough idea, the key principle here is that this is really, really, really good at pulling electrons away from things. That's why this happens. And why is this really good? Well, it turns out that these 9 protons are really not... The 9 protons are good at pulling on electrons. And in some atoms, the electrons that are present are really good at repelling electrons. The balance on this is that these are your big winners. These are not counteracted very much by these 7 electrons that are in the valence shell. The valence shell does not repel other electrons from coming in the same way that the 2 do here. The direction of the repulsion is minimized, canceled, and the net effect is that this is really, really good at taking electrons. So if I have something over here, and it has an electron, this will be really good at taking it. Okay? So this comes along and this takes an electron and brings it to here. Well, that gives it 8. Now the second thing is, the things that make this really good at taking electrons go away once it's taken that electron. So if I go to take a second electron, let's say this thing had 2 electrons to take, because I've put 8 electrons into here, there's no longer the capacity to put an electron into a spot under the same conditions. And when I go to put the next one in, it's going to need to go into a higher energy level. And so this is not pulled the same by these protons as this one was, because in addition to the same pull, we now have a significant repulsion from these electrons. And that changes the game. And so for that particular atom, the reason why this will get octet, the reason why this will become fluoride or chloride or bromide, or the reason why it'll share electrons with another halogen or something along those lines, is because it has the capacity for an electron, and it's really good at taking them. It does not do really well at taking multiple electrons. Okay? And if you go ahead and look at the opposite end of that spectrum, if we look at something like lithium, sodium, and potassium, and we draw a Bohr model of that, so here is our lithium atom. Well, let's go ahead and do sodium, so we're actually doing the octet. So sodium with its 11 protons, and it has 11 electrons. The electron that's here is very loosely held by these protons because in addition to this proton attraction, there's a significant amount of repulsion from those 10 electrons. And so on its own, the sodium is going to hold on to the electron, but just about anything else that comes along will be able to remove that electron from there and take it away. Okay? And when that happens, the next level has a significant amount of attraction to this. These electrons have the pull of this 11 protons, but they don't have a significant repulsion from each other. And so really the octet rule is a consequence of atoms that are really good at pulling on electrons and taking them, and atoms that are really good at releasing an electron and having them removed. And then those qualities change once you get past 8. But the number 8 is not special. And I want to emphasize this. The idea that these things have a capacity limit is great, and the fact that it works out to 8 for a lot of things is simple for chemistry. But in reality, there are many, many compounds where when you look at things like sulfur hexafluoride. Now, sulfur has a good chunk of protons. It does not have a significant electron repulsion compared to its proton attraction. So it's very good at taking electrons. Sulfur hexafluoride is a really cool chemical. If you breathe it in, you sound with a really deep voice. You can float things on it. It's invisible, so it looks like you would be floating them on air. Really cool stuff. If we look at this here, the sulfur here has 2 electrons here, 2 here, 2 here, 2 here, 2 here, and 2 here. And those are all being shared, but that's a total of 12 electrons. So we violated our octet rule, and there was no magic involved, there was no secret. The idea was that the sulfur is very good at pulling on electrons, and it has the capacity for it. Now what's the difference with sulfur and something else? Well, sulfur, if we look at its electron configuration, it is 1s2, 2s2, 2p6, 3s2, 3p4. And what that implies then is that very close to these orbitals here, there's an empty set of 3d orbitals. They have the capacity for a lot more electrons, and when this works in bonding, this is capable of using those orbitals, and it can then exceed the number 8. So the number 8 is just a basis of how the s and p orbitals function in terms of capacity. Anything that has d orbitals easily accessible, so anything in the 3rd period or above, is going to be able to exceed that amount. And so it's not a magical number 8. It works out for the first couple rows every time, with a few exceptions, and beyond that, it really doesn't hold. Sometimes it holds, sometimes it doesn't. And so I want to stress to you that this idea that atoms are happy with 8 electrons or things like that, another common one that we see a lot is that if we're looking at orbitals and we see this, that somehow that atom is unhappy or unsatisfied or angry or whatever until it gets that extra electron, and the idea that if there's an electron there, that will somehow stabilize the molecule. And that's not true. One of the things that comes into a big play is we look at electron configuration, I'm sorry, not electron configuration, ionization energy exceptions. So for example, if this is oxygen's 2p orbitals and this is nitrogen's 2p orbitals, this electron is easier to remove than that electron, which violates our trend. Usually as you move across the row, ionization energy goes up, becomes more difficult. And why would that be? So a lot of people will then take that and say, well, octet rule type philosophy. This is full and these are half full and the atom's unstable, it's unbalanced, something. That's not true. The reality is these 2 electrons are very close within that orbital state, and therefore they repel each other a lot. So if this is pushing a lot on this and this is pushing a lot on that, that makes it a lot easier to remove that electron because it's already being pushed out of the atom. So when I come along, I don't have to pull as hard because it's being pushed so much. There's nothing in the vicinity of this like there is for these 2. And so this one, I have to exert more energy, I have to exert more force to be able to remove it. It's not something magical, it's just electrons and protons attracting and repelling and capacity. Okay? So, if we go through and look, there are a lot of exceptions to the octet. There are a lot of things that you're not going to be able to get to 8 electrons. They just don't have the sheer numbers to be able to do it. It's not because there's some loser atom that can only have 2 electrons or something along those lines. It's because they just don't have the proton capabilities to attract that many electrons. For lithium, to get 8 electrons in its valence, it would have to pull in 7 electrons. It has 3 protons. And it has 3 electrons to start. You can't pull 10 electrons in towards 3 protons successfully. It's just not going to happen. Okay? So this is not something that we should just dismiss and say, oh, this is an exception to the octet. This is following in our scheme of protons and electrons attracting each other in capacity. This makes total sense for lithium to not end up with 8 electrons. Same thing with things like hydrogen, beryllium, and boron. Although boron can end up with 8 because it has that capacity available for it to attract more electrons, although it's not the most stable of compounds when it does get to 8. Okay? There are a ton of things that can violate the too many electrons, more than 8 electrons. Why? The key idea here is they have a d orbital capacity. If you're doing bonding and here's your 3s and here's your 3p, okay, and you don't have 4s electrons, then those 3d orbitals are not far off. And so these are accessible for you to use in that bonding. Now if you go with something that's in the 2s and 2p, and here are your 3d orbitals, well no, this is not going to work. This is going to be too difficult to put an electron into because it's going to be too far removed from your protons, and you're not having enough protons at that point to occupy that state in a stable fashion. Okay? And then of course odd number electrons, just physically there's no way to split those up. So what I want to do is I just want to kind of debunk any of the myths that the octet rule is some kind of special magical thing. It's really very simple. It's just protons and electrons attracting, electrons and electrons repelling, and what kind of capacity an atom has. And I think that we kind of grant 8 to be this special magical thing, when really that's just the case for some types. Okay, and there's a lot of exceptions to that, so really it should not be thought of as kind of a hard, fast rule that leads us down paths that are not so good. We want to look at each thing in a specific scenario, and a lot of times it will end up with those atoms end up with 8 valence electrons. Okay, but the reason why is because they have the ability to pull in electrons well, or they don't have the ability to pull in electrons. They have a lot of repulsion, so they're losing electrons. And then the actual physical capacity of the orbital states, whether in bonding or without, only allows us to be at 8.